So in mechanical engineering, we try to stay away from circuits when we can. As you can tell with systems, we don't always have that ability. One thing that's definitely our domain and not that of the EEs are motors. So we want to talk about electromechanical system and how we can combine electrical and mechanical systems. So if we have a motor, we can say that we have an armature voltage that is input to the motor system, and it acts with a resistance and inductor, and then we have a back EMF, EB. That back EMF is what causes a torque to adjust a motor. The motor might have some torque applied if it's doing the task, and it might have some friction that prevents it from rotating, so we can say that as a torsional damping is how we represent that. And we can combine these two systems through two variables, our back EMF constant, KB, and our torque constant, KT. Those will always be given to you. They're just constants that represent the relationship between our circuit and our motor. So we can go straight to the Laplace domain to talk about what's happening in our circuit. And we take the givens of our motor system, then we can do our summation of our torques is equal to our mass moment of inertia J times our angular acceleration, omega dot. And for this we have two inputs, torque and our input voltage. We have three main variables, and we have a bunch of constants. I think I forgot to underline KB over there. And we also have LA and RA are constants. Oh, I have that written up there, but I did not underline them. So we want to make sense of this by using multi-input, single-output systems. Our output is, from our point of view, we care more about the angular acceleration. So we could say that our output is omega, and we want to get rid of the variables of the back EMF and our current because those aren't of interest to us. Write those equations of motion again. We'll have everything in the Laplace domain, initial condition set to 0, and we can have everything simplified as much as possible by just writing things in terms of KT and KB, omega, and IA. And if we want to find our omega with torque as our input, it becomes a multi-input, multi-output, single-output system. So what we need to do is we need to consider that other input voltage and set it equal to 0. Then we can isolate our current, plug that into our second equation, and find a transfer function through algebra. And we're going to be able to get a transfer function that way, where we could say that our output angular velocity is equal to, over our input torque is LAS plus RA divided by JS plus B times LAS plus RA plus KT KB. If instead of looking at the effect of our angular velocity on our input torque, we wanted to look at our angular velocity based off of our input voltage, then we could set our torque equal to 0, and that's going to cause IA of S to be equal to J S plus B omega S divided by KT instead of what it was represented when our voltage was equal to 0. And then you could go through that again. And that's the example we did in class, was through our input voltage. And I will put that up on Canvas. Okay.